All right, I think we get started. Welcome everybody to this talk about reactive microservices with Akka and Docker. As many buzzwords as possible in one short title. My name is Heiko. I'm working for the fantastic company CodeCentric. We are a sponsor. Check out our booth if you want to talk. By the way, I'm also the author of this little German Scala book, so we give it away at our booth if you're interested. So, what is reactive? Who has read the Reactive Manifesto? Show me your hands. Most of you, that's great. Just in a nutshell, reactive defines a couple of traits or qualities which modern systems should have. And the most important of these traits is responsive, which means that a system should always respond to requests, if possible at all. And apart from a lot of functional requirements, there are two really important non-functional qualities that are required to be responsive, and that is resilient. So a system should stay responsive even in the face of failure. And elastic means that the system remains responsive under load. And if you put message-driven to the whole thing, underpin it with asynchronous message passing, you can enable these other traits. For example, because message passing means that you decouple the sender from the receiver, and you can have delegation of failure handling and all these cool things. Next question, what's a microservice? So for me, the size doesn't matter, but for me, it's more of the Unix philosophy. Do one thing, hopefully do it well. And one other really important aspect for me is that a microservice should be able to react or to act autonomously. And that means it has to be isolated from others, it has to be self-contained, and it needs to own its data. And we will see what that means with one example later. By the way, this booklet by Jonas Bonner has inspired a lot of the ideas and terminology I'm using here. If you haven't read that, check it out. It's a quick read. So, if you have a microservice, that doesn't really give you too much. You need a lot of microservices. They need to collaborate. And in this book, Jonas says one microservice is no microservice, they come in system. And this quote is actually stolen from, it goes back to various until biology people. And I think it's really important to understand that for this sort of collaboration, we have to think about how exactly that should happen. In a synchronous fashion or asynchronously? Or, yeah. Let's take a look later in detail. But for me, it is totally clear that in order to have autonomy, those microservices must be isolated. And you can achieve isolation using asynchronous messaging, asynchronous communication, because that decouples your services in time. So that means that you don't have to wait for the other service to be available to talk to it. And you can also contain failure, you can compartmentalize your system. So what I really want to convey is that one microservice should not access another one in a synchronous fashion when serving requests, because that would totally break isolation. That would mean no more autonomy. So for a reactive microservice, this is a no-go. So how does Akka fit into this picture? I think the ACTA model is a really great fit for any sort of reactive system, whether a microservice or not. If you look at Akka, it's not a single jar anymore. It offers you really a lot of high-level modules for scalability and resilience. For example, you can use Akka HTTP, which has been released in Akka 2.4.2 a couple of months ago. And that is really something you probably need for almost every microservice, right? Usually they have a HTTP API. And there's another module, it's called Akka SSE, Service and Events, which I initially authored. This is really great for asynchronous event-based collaboration, as we will see later in the example. Next question, how does Docker fit? First of all, containers provide isolation. Maybe not perfect isolation, but at least some sort of isolation on a host. And in my opinion, using containers and the Docker workflow, the container workflow makes the automation of the life cycle a lot easier. If you look at Docker in particular, there's a lot of tools and infrastructure available, namely Docker Compose and Docker Cloud. You should check out Docker Cloud, it's really pretty awesome. Okay, so the rest of the talk I will show you a demo. It's, of course, a very simple chat application. And there will be two services. There will be a user service to identify users, and then there will be a chat service that needs some information from that user service. And I want to show you how the chat service can get access to those information. We get there step by step. So I will sit down because I have to do some hacking and coding, so that's easier when sitting. I hope that's okay for you. So the first thing I would like to show you is just Akka HTTP, how to run a server. So there's two things you need to do. You need to bind to a socket, and you need to handle requests by sending responses, right? And those handlers are implemented using Akka streams. They are a flow, which is a linear processing pipeline, taking requests and emitting responses. But you don't have to really dive into the details of the Akka Streams API. There's a nice routing DSL, which can be used. And I want to show you how to build a really very, very simple web service. We call it the user API. So one thing you need to do is you use the HTTP API of Akka HTTP, called the bind and handle method, with a route. And you give it an address and a port, and then you react to either a successful server binding or a failure. But that's all you need to get the service started. The interesting part is here in this route. And this method apply creates the route. And currently, it doesn't really do a lot of things. But it hopefully shows you the nature or the feel of this DSL. The directives which are used here are a path matching directive to match the root path, the single/path. And then we only filter GET requests. Of course, there's POST and DELETE and all the HTTP verbs. And if such a request comes in, we complete it, which means we create a response with hello world. Great, huh? Okay, that's how it looks. And in order to run it on Docker, I have to show you how to create Docker images. So this can be done with SBT and the fantastic SBT native packager plugin. The guys downstairs from Gute Frage have SBT native packager t-shirts. Go and grab them, they are awesome. And with that really smart plugin, you just have some settings in your project, and then using the task publish local or publish, you can really create your Docker images. So let me show you that. First of all, let's take a look at the build.sbt file, where you have to put a couple of settings for Docker. And as you can see, probably the most important one here, the base image using Java 8. And with that in place, you can then do Docker publish local. And if you're familiar with Docker, you probably know these print lines. And now we have a latest version of the Gabler user service. So let's run it. I have a simple script. Let me show you this script that essentially just wraps the Docker run command with a couple of flags that are necessary. In particular, I want to expose the port to the host. I want to publish the exposed port to the host so I can access it. So if I do a run Gabler user, a Docker container is started. I can check out the log, and that looks good. So it seems to listen. So let me check out what happens if I call that. Oh, I don't need that. I just used the root path, and I get my hello world. So yeah, Akka is up and running on Docker. Of course, a proper user service would not only say hello world, but instead it would consume and create properly formatted requests and responses. And usually HTTP uses JSON, and Akka HTTP has a really neat feature. It's called marshalling, which means you can complete your requests with normal domain objects. We have already seen that. In our case here, the domain object was a string. But you might have asked yourself, oh, why can I complete a request with a string? I mean, I need a HTTP response, right? So what you really need type-wise is a to-response marshallable, something that can be marshaled as a response. And of course, strings can be marshaled. The response will be a strict entity, and the code will be a 200 OK, and it will be encoding text plain, all these things. If you do JSON marshalling, you of course have to tell Akka HTTP how to exactly marshal your domain objects. And Akka supports spray JSON and XML and JSON out of the box. And there's another project which I have started, and which is a great example of a community-driven project, because I didn't write that much code. It's all the other contributors. Akka HTTP JSON supports additional JSON libraries like Circe, PlayJSON, and so on. I personally really like Circe because it has a fantastic feature I will show you in a moment to automatically create the decoders and encoders, or the marshalling infrastructure which is needed for case classes and also for sealed trait hierarchies. So that's really pretty awesome. So let me just show you how a complete user service would look like. So we are now talking to a user repository, but the most important aspect here is that we're using more of the directives to properly implement a couple of API features. So when we get a user's path, which is then ended, we get by completing with a future. So we ask, this is the ask pattern, right, from Akka. We ask the user repository, get users, and the message we will get back is a users object, which is just a set of user, or wrapping a set of user. With that in place, we can complete the request. We can complete the request with a set of users, with a set of our domain instances. And that works because of these two imports. There's just the Circe import, which comes from the Akka HTTP JSON library, and you also need this auto magic import that makes all the heavy lifting possible. To be honest, that comes at a price. There are macros working under the hood, so the compile time will be even worse, right? It will become slower. You know, it's already pretty slow, Scala compiler. So, but it's very convenient. You don't have to do anything to your case classes, and if you really want, you can write those decoders and encoders manually. apart from getting users, we of course also have the ability to post users in order to create new users. And here I have something which I call a diverging response, because if I send this add user message to the user repository, there are two possible outcomes. Well, there's also the failure case, because I get like a future. But in the successful case, I could get a message, a response, username taken, or an event user added, right? So I need to deal with that by matching on the diverging options. But that can be done with the onSuccess directive. And yeah, I don't want to dive into all the details, but hopefully you can see that there's a couple of directives which are really powerful, which give you a lot of flexibility and power to, well, build your routes. Let me just build that again, and okay, we have it, no? Okay, now we have it. Okay, so let me again start the user service, take a look at the logs. Okay, that looks good. And now we can do the following. We can first just try to access the current users, which gives us back an empty array, and then we could, for example, create a first user, and that worked well. So if I try to get again, I get an array with one element, and you can figure out how the marshalling works for case classes. It's trivial, just mapping the parameters, the fields, to keys in this JSON object. And if I try to add the same user again, we get username taken, all these things. So Akka HTTP takes care of a lot of things, content type, content negotiation, and you even get nice status codes and all these things. Okay, great. Now we have a system which does what it should do. I mean, it is possible to add users and remove users, all these things, but it's of course not yet reactive. Why? Because if I just do a remove for this container, sorry, it's gone. It's no longer available, so it's not really super reactive. It's not resilient. So we need to take care of that. And one important piece here is the persistence of the state of actors. I haven't shown you in detail how this user repository is implemented, but it's just an actor, right? So you send messages to it, you add user and delete user, and it has an internal state. And once you stop that actor or just crash the whole system, that state is gone. And the question we have to answer is, how can we recover? How can we restore the state when we restart an actor or start an actor? And the answer is Akka persistence is event sourcing. Who's familiar with event sourcing? Okay, most of you. So for the others, in a nutshell, event sourcing is really different from traditional, let's say, create an update persistence, because you never delete anything, you never overwrite anything. Instead of storing the state, you store all the state changes, which are expressed as or modeled as events. So in Akka persistence, we would create an event for any valid command. A valid command would be add user with a username which hasn't been taken yet, okay, which is still free. And then we create an event called user added. And then we let the journal persist the event. The journal is the abstraction provided by Akka persistence for the database. It could be any database. I would say currently the Cassandra plugin for the journal is probably the most production ready. There's also a very good Kafka-based one. And there's a couple of local ones, which are not that interesting for me, because if I want to build a reactive system, I have to really go and build a distributed system. And therefore, I think a distributed database is the best option. But anyway, there's a journal abstraction. When the journal comes back to us here and acknowledges that the event has been persisted, we then, and only then, apply the event to the actor's state. That's the whole idea here. It's pretty simple. And whenever an actor, which is a persistent actor, gets started, all the events are replayed. So it ends up in the old state, the state in which it was before. There's so much more to say. You can do time travels by not replaying all the events. There are snapshots to avoid huge recovery delays, because if you have to replay millions and millions of events, that might just take too long. So there's a lot to say, which I don't have time for, but therefore I just want to give you a quick glance into how you would write that code. So let's take a look at the user repository. So as you can see here, we are extending persistent actor. That's the trait or abstract class we have to extend from. And a persistence actor has a persistence ID that has to be stable, that assigns the events for this particular actor in the journal. And then it has two receive methods. One is called receive command, which is just for the normal messages. I would say that replaces the receive. So if there's a command which is not related to persistence at all, like get users, we can just handle it like we did before. And if we get a persistence-aware command like add user, remove user, for example, add user is handled here in the add user method, we first validate the command. Is it valid? Can we add a user? So if the user already contains the username, we cannot. So that's an unvalid command, and we send back the bad confirmation, username taken. But else, we invoke the persist method. That tells the journal to take this event, user added, and store it. And only when the journal gets back to us, it will invoke this callback. And in this callback, we do two things. First, we change the state by invoking receive recover. Receive recover is also the method that is invoked for recovery. And therefore, we achieve getting into the same state again on recovery. And after that, we do some side effects like logging and sending messages. Okay? So it's important to understand that only after successful persistence, we apply the state, the internal state changes. And that's the pattern. And once we have that in place, we can give it a try. So let me first remove the current running thingy. I also have to start Cassandra or some journal, which I'm doing. I'm using Cassandra here. I have to check the log because Cassandra is really a little slow in starting. Okay, looks good. Now it has started, and now let me just run the Gably user again. Yeah, that looks good. Okay. And then curl, get the users, empty. Now let's add a user. Okay, add it. Looks good. We can now just remove the container. Let's just simply crash it and start it again and see what happens. If we try to get the users again, oh hooray! The user has survived the crash because we have used a persistent actor. So that's already getting us closer to a really reactive microservice. But there's more work to do. So what we need next is, okay, here, I already mentioned that. If we really want to have a reactive system, we need to distribute it. We need to have multiple nodes. We want to use Akka remote, we want to use Akka cluster. In Docker, you have so-called networks that isolate the containers. So within a network, containers can talk to each other. And if you want to externally communicate, you need to publish ports. And If you go for a multi-host deployment, I highly recommend using overlay networks, like supported by Docker Cloud, by CoreOS, and so on, because then you have like a virtual network where those those containers can talk to each other. You don't have to distinguish between public and bound address in Akka Remote. So Akka Remote introduced a feature where you can have a bind address and a published address, which is great if you cannot use overlay networks, but with an overlay network, you just don't have to worry. You don't need that nice feature. Okay, so in order to become reactive with Akka Cluster, we need to use the cluster actor ref provider. Akka is distributed by default, so everything should work in a distributed setting. Most of the things you have to do is just configuration. One thing to note is that in order to form a cluster, there's an approach using so-called seed nodes, which are, and in the Docker case, those container addresses are not known up front. So you cannot use seed nodes like you would do in a more static setting. And there's a library called Constructor, which I have authored, that helps with bootstrapping an Akka cluster. So if you have a coordination service like etcd or Zookeeper or Consul, that is used by Constructor, and the existing nodes of the cluster are looked up there, and bootstrapping all the corner cases are hopefully covered. I don't have the time to really show you the details of the state machine, but anyway, that library helps with constructing an Akka cluster. And with that in place, we now can use one or more of those high-level modules which Akka cluster gives you. And one is the cluster tools library. It has the cluster singleton implementation. And that is to run exactly one actor instance in the whole cluster. Well, not exactly. At most, it's more precise. So there's a cluster singleton manager, and that will manage the life cycle of this singleton actor. So if that goes away for whatever reason, it is started on an existing node again. So you really don't know where this actor is living, and therefore you need the cluster singleton proxy to talk to your actor, to your singleton actor. Let me show you how to do that. So in the app, in this class, which has a main method, where we just create an actor system and then create a root actor, which does all the other things, we create our user repository, sorry, here it is, the user repository actor, not directly as a child actor of the root like we did before, but instead we use the cluster singleton manager, which is started on every node, and therefore via communication with its peers knows where to create that singleton. It's usually it is the oldest node, and only if that goes away, it will create a new one. Okay, so let's see how that works. So what we can do now is we can run Gabler user with the default port and also with another port. So what that gives us, hopefully, is that we can access the users. Oh, great. That is no good. Okay, Docker logs -f Gabler user 0. Ah, yeah, I see. So I mentioned this nice little library to bootstrap the cluster called Constructor. Do you remember what it needs? A coordination service. So I have to run etcd. Okay. Let me do that exercise again. So we have Cassandra, we have etcd, And now I'm trying to start a gabbler again. Go away, please. Okay. Now I have really high confidence that it is working. Yes, great. So this one is working. Let's create another one. And curl it. Hooray! So I'll do it again. We can either call the one or the other, and both of these running services will give us one user. And that is because the user repository is really only running once in the cluster. And I can, so the oldest one was the first, so I can kill one of the nodes. It is Gabler user 0, and still the system should be available, as you can see here. So everything is fine. Cluster singleton helps with that. And now we enter a library and a pattern which is really neat for event-based collaboration of services, because what we have seen was a single service, and as I said, Jonas said, one microservice, no service. So we need those services to collaborate, and service and events, I think, are a nice way to do that. I just noticed that, I don't know, half a year ago, because usually service and events are just for pushing events to the browser. It's a standardized API, and it's supported by most every reasonable browser, and yeah, so it's a very, very simple protocol, completely based on HTTP. You do a GET, and then the server responds with a response which is kept open. It's not closed, so it's almost like long polling, but standardized. And the content type has to be text event stream, and the events themselves are really simple new line based, text-based things, UTF-8. So that is a neat way to communicate or to let them collaborate. So what I want to show you next is how to implement a way to publish user events. I mean, when we create a new user, or if we remove a new user, that needs to be published to interested parties, to other services, right? And that can be done using service and events. So let me show you that. So the user API is here, and let me just compile that, so it's getting faster later. Our route, which is shown here, not only contains the users, it now also contains the users' events. And this route is a little more complicated because in the service and event specification, the client could send a header called last event ID, which the server then should treat in a way to only start pushing the events from that last event ID. And that is optional, so we have to deal with that. So, but what we are doing here is we go to the user repository, we tell it, or we ask it to get the user events from the sequence number, which is defined by the last event ID, and we map it to user events. User event is just another element or class in our domain model, as you can see here. And then we map the user events to server sent event, which is essentially a case class you can see here, provided by the Akka SSE library. With that in place, as you can see here, we can complete the request. So what we are really doing here is we complete the request with a source of server sent events. So if you look at the type here, oh, it's a future. Okay, anyway, future is great too. So we can complete requests with futures, as you have seen before. And in this case here, when we map it to server-sent event, Akka SSE takes care of the marshalling and treating those events when they arrive as needed. Okay, so let's check that out. Has been built. I run it. What's that? Constructor. It's not creating the system. Okay, I will just abort everything. Those pesky live demos. Let me run etcd. Let me run Cassandra. And maybe this state of the example is broken, so I will even move forward to the next state. And I have tested that before, so I know it's working. Okay, so what we are getting at now is two services collaborating. And I will show you this, how such an event stream looks like. But the base idea is the following. If you have two services where the user events come from the right side, your client, your service which is consuming them, should just, well, run in a loop and consume the events as they arrive. And if the connection breaks or for whatever reason is closed, it just reconnects. And it uses this last event ID. So any client of the user service interested in user events would collect those and extract the data it needs and store the data in its own database. I mean, this is the idea of autonomy, right? A service needs to own its data. And in the case of the chat service, now we have a second project here, and the chat service also has a repository for users, so it takes care of storing the users, but you cannot add users to the chat service directly. This is done by going to the user events from the user service. So as you can see here, the user repository of the chat service has a URI which it uses to connect to the user service and get the events. This is abstracted away in this server-sent event client, which does all the heavy lifting with the reconnection if the connection is dropped, all these things. So it's quite interesting stuff with a graph. So it's not a simple flow, not a linear processing pipeline, but Akka streams used as a cyclic graph. Pretty interesting stuff. You can take a look if you're interested. Yeah, to make that easy to use, I have abstracted it away in this simple service and event client. And what I'm going to show now is the following. If I really start two of those services, so what I'm going to do is now I run the Gabler user, and I also run the Gabler chat, and I hope, what? Oh, I have to build it. Ah, maybe that was my mistake before. I don't know. So let me publish local. Okay, now both images should have been built. So I run the user service and I run the chat service. My script doesn't remove the old one, that's bad. But now, okay, Docker logs. Gabler chat. Up and running, that looks good. Gabler user, up and running, that looks good. So let's follow the chat here. So that's the chat service, and that is listening to events of the user service. So that means if we add a user to the user service, currently we only have 0 users because we restarted Cassandra. Now we add one, we add it, and oh, can you see it here? So it was pretty quick, huh? So this is the chat service, and it added the user with username 1, which had been added in this other service. So let me do that again. It is quick, but still, so if you look up here, it takes some time, like 2 seconds, 3 seconds. So it's asynchronous collaboration using events. And that brings me to the end of the talk. Everything is available online. In particular, the sample application I have shown you, the code I have shown you, under my GitHub, Heiko Seeberger, Seeberger account. And I think we have time for questions. Are there any questions? How do we do that? Do we have a mic for people who have questions? No? Okay.
Perhaps you can repeat the question.
Okay.
Hello? Oh, no, it works. So I have a question about the different services being autonomous. Do you create a cluster for each of those in Akka clustering, or do you have a shared cluster with multiple services in them? And
yeah, that's a very good question.
Yeah.
That's a very good question. So I didn't explain that. No, so each service is autonomous and could have or should have its own cluster. Because it's autonomous, it should not be in the same cluster. I mean, in Akka cluster, the membership to a cluster depends on the name of the active system. So if you name them differently, like the Gabler user and the Gabler chat, then they cannot be in the same cluster anyway. And I think that's a good thing. That's what you want, right? So each service should be autonomous, deploy to 2, 3, 4, 10 nodes, and that's it. Yeah. More questions?
Hello. Hello.
Hey.
How would you suggest dealing with serialization of the user model between, so from the chat to the Gabler, you sent the user model from one side to the other, so with context restriction.
The serialization.
Well, yeah, so how would you deal with handling the user object that you defined in the one application in the other application, and how would you share that definition? Or
yeah, so that's a really good question. It's a really hard problem because even if you solve it once, things might change. So if you think about serialization of data, either to Akka persistence or to another service to consume it, you might run into version problems if you change your object and therefore change the serialization format. You need to think about that upfront. You definitely need to think about that upfront. It's very, very important. And I think the way to treat it is the way in which we always treat like incompatible changes. So there might be compatible changes in JSON if you just add a field that should not break the user who doesn't even know that field. But if you rename a field, that's a breaking change. So then you should probably offer a second API, version 2, version 3, whatever. So you would then have to support, at least for some time, 2 versions of your API. So in this case, the user event stream, there would be 2 versions of that, 2 streams, right? One with the old and one with the new format, if they are not compatible. That's a really, technically it's easy to do, but for a product lifecycle manager, that's a hard thing and should be considered upfront.
So would you recommend tools like Protobuf? And
Sorry?
So would you recommend tools like protobuf or something to abstract away from the versioning that gives you some way to...
Maybe. I don't have a final answer to that, but definitely some tools like that or others. So. By the way, Akka does offer help with that, in particular with Akka persistence, where you really want to be able to restore the old events from last year or maybe from 10 years ago. There's an adapter layer in Akka persistence which you can and probably should use. All right, so we are running out of time. Thanks. You can catch me down at the booth or somewhere. Enjoy the rest of the conference, and yeah, thanks.